Hello and welcome to my science tutorials. In today's video, we want to look at a resistor-inductor series AC circuit, or what we normally just call RL series AC circuit. Before we begin, if you're new to my science tutorials, kindly consider subscribing and turning on that notification button so that you do not miss any of our latest tutorials on biology, chemistry, mathematics, and physics. Without further ado, let's begin. So an R and L series AC circuit, this is just the type of circuit that contains an inductor and a resistor as the main component or the major component. So if we draw the circuit diagram for this particular circuit, we have a resistor which is connected to an inductor, and then they are all connected to an AC source in this way. So the voltage across the inductor is what we call VL, which is the inductive voltage. So the inductor is L, the resistor is R. The voltage across the inductor is what we call the inductive voltage, and then the voltage across the resistor is what we call the resistive voltage. Now we have the total current passing through this entire circuit. Since they are in series, the same current pass through all of them, and then the voltage over here supplied by the source of AC is what we are calling the applied voltage. Now the applied voltage is the phasor sum of VR and VL over here. I'm going to be explaining what the phasor sum means later on in the tutorial. Now in this circuit, the current lags the applied voltage by an angle between 0 to 90 degrees. So we are saying that if we draw the phasor diagram for this particular circuit, we are going to have something that looks like this. We're going to have our resistive voltage over here. We're going to have our inductive voltage along this line. And then we're going to have our applied voltage is somewhere in between the resistive voltage and then the inductive voltage. Now, the angle it makes with the resistive voltage or the horizontal component of this axis, that angle is what we are calling the phasor angle. So this is what we call the phasor diagram. This is the phasor diagram. And then over here, this is our applied voltage. This is our circuit diagram. Now, from this phasor diagram, if we extend this to complete the triangle that we have over here, we can make some deductions from this particular phasor diagram. So we can have something we call the voltage triangle and then the impedance triangle from this phasor diagram. So let's have a look at that. So the first one I want to look at is what we call the voltage triangle. And it looks exactly like what we have over here. We have the phasor angle over here. This is 90 degrees over here because it's a right angle triangle. And since we have the VL on the vertical axis over here, it corresponds to the length over here as well. So we have our VL over here, the inductive voltage, and then we have our resistive voltage VR on the horizontal axis, and then the applied voltage on the hypotenuse side of this. Now, the applied voltage is equal to IZ. The Z over here is what we call the impedance, which is the overall opposition to the flow of current in any AC circuit. The inductive voltage over here is the product of the current multiplied by the inductive resistance XL, and then VR, like indirect current, we know is equal to IR, which is current multiplied by the resistor. Right, so this is what we are calling the voltage triangle. Voltage triangle. Now, another triangle we can get is what we are calling the impedance triangle. So from the impedance triangle, it is still just the same, only that over here we are looking at the impedance or the opposition to the flow of current. So we know that over here is supposed to be the applied voltage, but instead of that, we're going to put Z, which is the impedance of the entire circuit. Over here, we know we are supposed to, on this axis, the vertical axis over here, we are supposed to put the inductive voltage, but we're going to put the inductive reactance over here, and over here we're going to put R over here. So this is what we are calling our impedance triangle. Impedance triangle. Okay, and then our phasor angle is over here. Now, from these two angles, the voltage triangle and then the impedance triangle, we can make some calculations. So let's have a look at what we can find from these two angles. Let me use a blue color for that. So using Pythagoras theorem, from this voltage triangle, if we want to find the applied voltage, which is the hypotenuse over here, that will be equal to V squared is equal to VR squared plus VL squared. If we make V the subject, we are going to have the square root of VR squared plus VL squared. And now this is what we are calling the phasor sum. Okay, the phasor sum of the resistive voltage and then the inductive voltage to get the applied voltage. So we said that the applied voltage can be obtained by the phasor sum of the resistive voltage and the inductive voltage. And then this is what we are calling the phasor sum. Phasor sum. Either this or what I gave earlier on over here. So this is how we find the applied voltage in this particular case. Now let's get some space and look at how we find the angle or the phase angle over here. So let me quickly erase the circuit diagram over here. All right, so if we erase, now that we have this space, let's look at how we find the phasor angle over here. Now we can see that in this type of circuit, we only have our inductive voltage and then the resistive voltage. So this is the opposite side of the triangle. This is the adjacent side of the triangle. So the trigonometric ratio that will give us opposite and adjacent is what we call tan. So we have tan, the angle, the phasor angle, to be equal to the opposite, which is VL, over the adjacent, which is VR. So it means if we want to find our phasor angle, we just need to find the tan inverse of the ratio VL over VR. So this is one important equation you need to keep in mind, and then this is another very important equation you also need to keep in mind. Now, if we look at the impedance triangle, we can also do something similar to that. To find our overall impedance for the circuit, Z is going to be equal to Z squared is equal to XL squared plus R squared. Okay, this is plus. And then to make Z a subject, we're going to have square root of XL squared plus R squared. It doesn't matter which of this you bring first, whether R or XL, you're still going to get the same answer. So this is the formula that we use. Question 3, this is the formula that we use to find the impedance of the entire circuit. So the impedance is the total or the overall opposition to the flow of current in an AC circuit containing two or more components, such as maybe an inductor, resistor, or a capacitor. Now, from the impedance triangle, again, we can also find the phasor angle. So that will also give us tan theta, or tan the phasor angle, to be equal to the opposite and then the adjacent. So the opposite is the inductive reactance over the adjacent, which is the resistance over here that we have. So to find this, we just find the tan inverse of XL over R. So this is another equation that is also very, very important for us to look at. Now, one final touch to find the, let's say, the current in the entire circuit. If you are asked to find that, we know V is equal to IR, okay, from Ohm's law. Now in an AC circuit, or in this particular uh, example, we are looking at the applied voltage, which can be obtained by using the phasor sum of the resistive voltage and then the inductive voltage to be equal to the current, which is the same across all components. And then the opposition to the flow of current in this particular example is what we are calling the impedance, the Z over here. So it's IZ. Okay, and then we can find this Z by finding the square root of the inductive reactance squared plus the resistance squared. That is how we find the Z over here. So this is also another important formula that we'll be using along this tutorial. So equation number 1, equation number 2 or 4, 3 and 5, they are very, very important, and we are going to be using them in solving a lot of questions which will be coming very soon. All right, so now that we've covered the basics, let's look at some practical example or some problems and see how we apply these formulas or how we use them to solve questions. So problem number 1, we have in a series RL circuit, the potential difference across the resistor R is 12 volts and the potential difference across the inductor L is 5 volts. We are to find the supply voltage and the phase angle between the current and the voltage. So this is pretty easy. For us to enhance our understanding, let me draw this particular circuit. So we have a resistor R over here, and then we have an inductor L over here, and then this is connected to an AC source that has a voltage, applied voltage, this has a current. And then we are saying that the voltage across the resistor is 12 volts. So over here VR is equal to 12 volts. And then the voltage across the inductor, which is VL, is equal to 5 volts. All right, so now that we have this circuit diagram, we've been asked to find the supply voltage, which is the phasor sum of these two guys over here, and also find the phasor angle. That is, so if we draw the phasor diagram, we're going to have something that looks like this. We'll have our VR over here, and then we have our VL over here, and then our this V will be here, and this angle is what we are supposed to find. All right, so let's have a look at how we solve this problem. So the first thing we want to do is to code the formula of how to find the applied voltage. So to do that, we know V is equal to the square root of VR squared plus VL squared. Very easy, very straightforward. So we know V is equal to the root of our VR is 12 volts. So we have 12 squared plus our VL is 5. So we have 5 squared. So this is equal to, if we compute these into our calculator, we are going to get 13 volts as the answer for our supplied voltage. Now, the second part of this question is asking us to find the phase angle between the current and the voltage. To do that, we simply said tan the phase angle is equal to VL over VR, as we saw, or as we can derive from this particular diagram over here. This is opposite over adjacent, which is VR over here. We already know what our VL is. We already know what our VR is. So our angle is equal to the tan inverse of VL from the question is 5, and then VR from the question is 12. So our angle is, if we compute the tan inverse of the ratio 5 on 12, we are going to get 22.62 degrees. So this is how we solve a question involving an R and L circuit. Let's have a look at another example. Example number 2. A coil has a resistance 4 ohms and an inductance 9.55 millihenry. We are to calculate the reactance, which is the inductive reactance, the impedance, and the current taken from a 240 volt 50 hertz supply. We are also to determine the phase angle between the voltage and the current. All right, so this is very easy, very straightforward. Let's go ahead and write down our solution. So the first thing we want to do is to note the parameters that we have so that we know how we go around this calculation. So we've been told a coil has a resistance of 4 ohms. So our R is 4 ohms. It has an inductance L to be equal to 9.55 millihenry. So we are to calculate the impedance, the reactance, the current taken from a 240 volt. So we have our voltage to be 240 volts, applied voltage. We also have our frequency to be 50 hertz. All right. So the A aspect of this question is demanding that we find the reactance. The reactance in this case is the inductive reactance, which is XL. So XL, to find the inductive reactance of an inductor, it is given by the formula 2 pi FL. So this is equal to 2 pi. Our frequency is 50 hertz. Our L, the inductance, is 9.55 times 10 raised to the power -3. So if we compute everything over here into our calculator, we are going to get 3 ohms as our answer for the reactance. So let's go ahead and find B. The B is saying we should find the impedance. We know the impedance Z is equal to the square root of R squared plus XL squared. We just found XL to be 3, so that is a good news for us. So this is equal to our R, which is the resistance, is 4. So we have 4 squared plus our XL, which is the inductive reactance, is 3. So we have 3 squared. Now, if we compute everything over here into our calculator, we are going to get 5 ohms as the total opposition to the flow of current in this particular AC circuit. The C aspect of the question is demanding we find the current in this particular circuit. So we know voltage is equal to current multiplied by the impedance. This implies that our current is equal to the ratio of voltage to the impedance. And so this is also equal to, our current is equal to, our voltage is 240 volts, and then the impedance that we just found is 5 ohms. So our total current that passes through this particular circuit is going to be the ratio of 240 to 5, and that is going to give us 48 amperes. All right, so the final aspect of the question is asking us to find the phase angle. So this is very easy. So we know that our phase angle is tan. The phase angle is equal to either VL over VR, or we have XL over R. Now, because in this case, we don't have the inductive voltage and then the resistive voltage, we are going to be using XL over R. So we know our tan, the phase angle is XL over R, and the phase angle is tan inverse of our XL is 3 over here. Our R resistance is 4 over here. And so our phase angle is going to be tan inverse of 3 on 4. That is going to give us 36.87 degrees. So this is our phase angle for this particular problem. Now let's have a look at one final example. We have a coil of inductance 318.3 millihenry and negligible resistance being connected in series to a 200 ohms resistor and a 240 volt 50 hertz supply. We are to calculate the inductive reactance of the coil, the impedance of the circuit, the current in the circuit, the potential difference across each component, and then the phase angle. So this is very easy. So let's go ahead and write down our solution. Now, for the sake of those who might not be able to visualize this, let me try and draw the circuit diagram. So the circuit, we have a resistor, we have an inductor, and then we have an AC source over here. So this is how our diagram is going to be. Over here, we don't know the potential difference across each of the components. So VR and then the VL, we don't know. This is our resistor. This is our inductor L. The current I, we also don't know. But we know that the voltage is 240. And then we also have the frequency to be 50 hertz over here. We also know that the resistance is 200 ohms over here, and then the inductor is 318.3 millihenry. All right, so this is how our circuit diagram is going to look like. And then the first aspect of the question A is for us to find the inductive reactance, which is XL. And from the previous example that we did, we know that XL is equal to 2 pi FL. So with that in mind, we just write 2 pi FL and we do the necessary substitutions. We know our frequency has been given to be 50. We have 50 here. And then our inductance is 318.3 times 10 raised to the power minus 3. Okay, so if we compute that into our calculator, we are going to get the value of XL to be equal to 100 ohms. Now, the second aspect of the question is asking us to find the impedance. We know that the impedance is equal to the square root of R squared plus XL squared. So this is equal to the square root of the resistance, we know is 200 ohms, so we square that, plus we just found the inductive reactance to be 100, so we have 100 squared. Now, if we compute that into our calculator, our impedance is going to have a value of 223.61 ohms. Okay, now let's continue to look at the third aspect of this question. We have to find the current flowing through this circuit. So we know that V is equal to IZ. This implies that our current is equal to the ratio of voltage to the impedance. And this is equal to, our voltage is 240 volts, so we have 240. Our resistance, which is the impedance that we just found, is 223.61. So let's divide that by, let's divide 240 by 223.61. So if we compute that into our calculator, it's going to give us a value of 1.073 amperes as our current flowing through the circuit. Now, the D aspect of the question is demanding that we find the potential difference across each component, which is VR and VL over here. So let's do that. So for VR, which is the potential difference across the resistor, is going to be IR. And we found the I, which is the current, to be 1.073 multiplied by the resistance of the resistor is 200 over here. So if we do the multiplication, we are going to get, for our VR, we are going to get 214.6 volts as our answer. Now, the second one is VL. So VL, which is the inductive voltage, is the product of the current and then the inductive reactance. Just as before, our current is still 1.073 multiplied by our inductive reactance, we saw earlier on, was 100 ohms that we found at the top over here. So we have 100 over here. And so if we multiply this by this, we are going to get 107.3 volts. Now, here is a catch for you to verify if your answer is correct. We said that the applied voltage is the phasor sum of these two voltages, so which is VR squared plus VL squared. Now we just found out that our VR is 214, so 214.6 squared plus 107.3 squared. Compute this into your calculator and see whether you get anything close or 240. If you get 240 or 239 point maybe 8 something something, then this should tell you that our calculations that we've done so far up until this point, everything is correct. So that is just a quick hack. So try it and see if the answer is correct. If it is equal to 240, it means you are right. But if it is not, then it means the calculation we've done over here is wrong. So let me know your answer in the comment section below. All right, let's proceed to find the last aspect of this question, E, which is telling us to find the phase angle. So for the phase angle, we know tan the phase angle is equal to VL over VR. We just found these two guys, so we know this is equal to the tan inverse of our VL is 107.3, our VR is 214.6. So our phase angle is equal to the tan inverse of this ratio is going to give us 26.57 degrees. All right, so this is our phase angle, this is our inductive reactance, this is our impedance, this is our current, and these are our potential difference across the various components, that is the resistor and then the inductance. So thank you so much for watching, and I will see you in the next video. Bye bye. Hello and welcome to my science tutorials. In today's video, we want to look at problems involving RL series AC circuit. Now before we begin, if you're new to my science tutorials, kindly consider subscribing and turning on the notification button so that you do not miss any of our latest tutorials on biology, chemistry, mathematics, and physics. So without further ado, let's jump into today's video. Now, in our previous tutorial, we did look at R and L circuit, where we talked about all the important formulas and all the important things we need to know about this particular R and L circuit. So over there, we talk about the circuit diagram, the phasor diagram, the voltage triangle, and the impedance triangle. If you've not watched that video, I will leave a link in the description of this video so that you can go back and watch that. Now, once you are good to go, or you already have a fair idea of what an R and L circuit is made of, you are good to go and you are good to start this tutorial. All right, so we have a question here. A coil consists of a resistance of 100 ohms and an inductance of 200 millihenry. If an alternating voltage V given by V is equal to 200 times 500 T volts is applied across the coil, we are to calculate A, the circuit impedance, B, the current flowing through the circuit, C, the potential difference across the resistance, and D, the potential difference across the inductor, and lastly E, the phase angle between the voltage and the current. So this is very simple. So let's go ahead and look at the solution for this particular problem. All right, so we've been told that our coil consists of resistance. So we have our R is equal to 100 ohms, and L, which is our inductance, is 200 millihenry. We've been told that the voltage is given in a waveform which is equal to 200 sine 500 T, and so that is all we've been given, and we've been asked to find the impedance, the current, and all other parameters. Okay, so in an AC circuit, the voltage given in that particular wave format, or in this wave format, is not the voltage that we use. We use another voltage which we are calling the applied voltage, or the root mean square voltage. Now, From here, the general formula is given as V is equal to V naught sine 2 pi f t. So if this is our equation 1 and this is our equation 2, comparing equation 1 and equation 2, we can see that V naught is equal to the 200 over here, and also this is 200 volts, and then the 2 pi f over here is equal to the 500 we have over here. So 2 pi f is equal to the 500 we have over there. So that is in radians per second. Okay, now that we have this, to actually calculate the applied voltage in this particular circuit, which is our V that we'll be using for the calculation, this is equal to root 2 on 2 V naught, or 0.707 multiplied by V naught. This is how we find the voltage in this particular case. All right, so the first thing we've been asked to find is the impedance of the circuit. So we know that the impedance in an R and L circuit is equal to the root of the resistance squared plus the inductive reactance squared. But if we look at the parameters that we have the resistance, we have the inductance, but we don't have the inductive reactance. So we need to find that first. So XL is equal to, from our previous tutorial, we established the fact that XL is equal to 2 pi FL, where our F is the frequency, our L is the inductance that has been given to us over here. So from here, we can do the computation and we have our frequency. So from here, we can see that the 2 pi F that we have over here has been given to us to be 500. So instead of having this, let me quickly erase that. We've been given this as a group, so let's use that for the calculation. So our 2 pi F is now 500 multiplied by the inductance of the inductor, which is 200 millihenry. Milli is times 10 raised to the power -3. Okay, so if we compute this into our calculator, we are going to get 100 ohms as our inductive reactance. So now that we have our inductive reactance, we can just do the substitution back into this formula to get our impedance. So our impedance is going to be, our resistance is 100 squared plus another 100 squared, and this is going to give us the root of 100 squared plus 100 squared is equal to 141.4 ohms. So this is the impedance of the entire circuit. Now, the B aspect of this question is asking us to find the current that is flowing through the circuit. So we know that our voltage, or the root mean square voltage, is equal to IZ. We know our Z, which is the impedance, but we don't know our voltage. But remember, I said that our voltage, which is this voltage over here, is equal to this formula, which I'm saying root 2 on 2 V naught, or 0.707 V naught. So I'm going to use the 0.707 multiplied by the V naught, which we got from this expression that has been given to us in the question. And we established the fact that the V naught, comparing these two equations, is equal to 200. So this will be multiplied by 200. So if we compute that into our calculator, we are going to get 141.4 ohms volts as our voltage. Now that we've established that fact, we can now go ahead and make current the subject over here. So if we make current the subject, we are going to have the ratio of voltage to the impedance. Now the voltage we have is 141.4, and then the impedance is also the same thing, 141.4. So this is going to give us a current of 1 amperes. Now, the next thing we want to look at is the C aspect, which is the potential difference across the resistance, and then the potential difference across the inductor. So let me get some space, and then we continue. All right, very good. So our C, we are to find the potential difference across the resistor. The potential difference across the resistor is denoted by VR, and then it's equal to IR, just like in Ohm's law. So this is going to be equal to, our current is 1, and then our resistance, which has been given in the question to be 100, is over here. So it means our potential difference VR is equal to 100 volts. Now let's move to D. We have to find the potential difference across the inductance. So VL. Now VL is equal to IXL, where I is the current and then XL is the opposition to the flow of current in this particular circuit when there is an inductor. So it's inductive reactance XL. So from here we know our current is 1, and then our inductance XL, inductive reactance, is also 100. So we have 100 here. So this is also going to give us 100 volts. All right, now we did some calculation over here, and then we said that our voltage, which is the applied voltage for the entire circuit, is 141. So if we do a quick cross check to see whether this is true, applied voltage is equal to the root of VR squared plus VL squared. So that V is equal to the root of 100 squared, which is VR, what we found over here, plus VL, which is also 100 squared. And so if we compute this into the calculator, we are going to get 141.4 volts, which is equal to what we found over here earlier on. All right, so let's look at the last aspect of this particular question. That is asking us to find the phase angle between the voltage and the current. Now, to find the phase angle between the current and the voltage, it is given by the formula tan the phase angle is equal to VL over VR. Now that we have this, we can make the phase angle the subject by taking the tan inverse of the ratio VL over VR. Now the angle is now equal to the tan inverse of 100, which is the VL over here. Sorry, this is 100 volts. Okay, so this is 100 over 100, which is 1. And then the tan inverse of 1 is equal to 45 degrees. So it means the phasor angle, or the phase angle between the voltage and then the current, is at an angle 45 degrees. All right, let's have a look at another problem. We have a pure inductance of 1.273 millihenry is connected in series to a pure resistance of 30 ohms. If the frequency of the sinusoidal supply is 5 kilohertz and the potential difference across the 30 resistor is 6 volts, we are to determine the value of the supply voltage and the voltage across the 1.273 millihenry inductance. We are also to draw the phasor diagram. Okay, so this is pretty easy. Let's go ahead and jump into the solution for this particular problem. So to enhance our understanding of this question, let's draw the circuit. So we have a resistor R, and then we have an inductance connected to an AC source over here. So this is our inductance L. We are saying we have an inductance of an inductor of an inductance 1.273 millihenry. We have connected to a pure resistance of 30 ohms. So this is 30 ohms. We've been told that the frequency over here is 5 kilohertz. And we've also been told that the potential difference across the resistor, the 30 ohm resistor, is 6 volts. So it means that VR is equal to 6 volts over here. and then VL, we don't know what VL is. And so we have to calculate the applied voltage, which is the entire voltage over here, and then the voltage across this particular inductor. So this is very easy. Let's go ahead and look at how we do that. Now, in this AC circuit, because the components are connected in series, the same current flows through all of them. And so since we have the resistance over here, the voltage across this component, we also know that we can use these two guys to find the current, and that will be the same current for the entire circuit. So let's go ahead and do that. We know VR, which is the resistive voltage, is equal to IR. So from here, we make current the subject, we get VR over R, and that is equal to VR is 6, which is 6 over here. Then the resistance of the resistor is 30. So if we do the computation, we are going to get 0.2 amperes as the current flowing through this entire circuit. Now, the next thing we want to do is to find the supply voltage. Okay, so for us to find the supply voltage over here, know that the supply voltage is given to us as V is equal to IZ, where Z is the impedance of the entire circuit. Now we've already found the current, but we do not know our impedance, so we need to find our impedance. But our impedance is given to us as the root of the resistance squared plus the inductive reactance squared. Here again, we realize that we do not also know our inductive reactance, so we have to find that. So our inductive reactance is given mathematically as 2 pi FL. So this is 2 pi. Our frequency we've been given to be 5 kilohertz, so we have 5 times 10 to the power 3 multiplied by our inductance, which is L, which has been given to us to be 1.273 times 10 to the power minus 3 over here. So our XL, if we compute entire of this into our calculator, we are going to get 40 ohms as our answer. So now that we have this to be 40 ohms, we can calculate our impedance. So Z is equal to the root of R is 30, so we have 30 squared plus 40 squared. So if we compute this side into our calculator and find the root, we are going to get 50 ohms as our impedance. So now that we have the impedance, we can just go and do the substitution back to equation 1 to find our supply voltage. So we know that our current is 0.2, which is what we found over here. And then our impedance is 50. So we just multiply the 2 to get our voltage. So 0.2 multiplied by 50 is going to give us 10 volts as our answer. So we have that as the supply voltage. Now let's find the voltage across the inductance that we have over here, VL. So let me do that at the top corner over here. So VL will be equal to IXL, the current multiplied by the inductive reactance. Now we already know the current to be 0.2, and then we just found the inductive reactance along the process when we're finding the impedance. So that is 40. So we use that to multiply it. So it's 0.2 multiplied by 40, and that is going to give us 8 volts. So the voltage across this inductor is 8 volts. Now, to draw the phasor diagram, this is pretty easy. So let's go ahead and look at how we draw the phasor diagram for this problem. Okay. So the phasor diagram of an R and L series AC circuit looks something like this. And then we have the applied voltage V itself over here, and then we found that to be 10V. We have the resistive voltage VR at the base over here, that was found to be 6 volts. And then we also found our VL to be 8 volts. That is also at the top over here. Now, at the bottom over here as well, current is also flowing in the direction of the resistive voltage. So we have current over here to be equal to 0.2 amperes. So we can just extend these guys to meet this guy over here, and then this angle becomes our phase angle. So this diagram is what we are calling a phasor diagram. So this is our phasor diagram for this particular problem. Now let's have a look at one more final example. So problem number 3. A coil of inductance 159.2 millihenry and resistance 20 ohms is connected in series with a 60 ohm resistor to a 240 volt 50 hertz supply. We are to determine A, the impedance of the circuit, B, the current in the circuit, C, the circuit phase angle, D, the potential difference across the 60 ohm resistor, and E, the potential difference across the coil. So this is a very interesting question. So let's go ahead and write down our solution. Now, for us to understand this particular question, let's have a look at the parameters that we have. So we've been told a coil has an inductance. So we have a coil, okay, that has an inductance L to be equal to 159.2 millihenry. And the same coil has some internal resistance or a resistance of 20 ohms. And then the circuit itself has, the coil is connected to a resistor, okay, an external resistor, which has 60 ohms. And then we have a voltage of 240 volts, 50 hertz supply. All right. So if we do this combination, our circuit diagram is going to look something like this. So we have a resistor and an inductor connected to another resistor, and then connected to an AC source. So the AC source has the voltage 240 volts and then 50 hertz supply. We have our current, which we do not know, and then we have our resistance over here. So this part is the coil. So let me use these dotted lines to indicate that. So this side is the coil. So the coil is made up of the resistance, which is resistor 20 ohms, and then an inductance of 159. So we have 159.2 millihenry. Then we have an external resistor here, R, it will be equal to 60 ohms over here. So the voltage across the coil over here, this side, is what we call V coil, or the applied potential difference across the coil. And then the applied potential difference across this resistor is VR, as usual. So this is our circuit diagram. But we can simplify this entire circuit diagram to become something like this. Because this resistor and this resistor are in series, okay, and we know in series we add the resistance. So the total resistance over here is going to be 80, and then connected to an inductor, and then connected to an AC source. So over here we have our current here, we have our inductance here to be 159.2 millihenry. So we can simplify this entire circuit as something that looks like this. All right, so now that we are done drawing the circuit diagram and we've fairly understood the components that we have, let's go ahead and answer the questions that follow. So A, we are to find the impedance of the circuit. Now, to find the impedance of this circuit, we need to critically look at what we have. We have two resistors and then one inductor. Okay, so our resistance, the resistance in this entire circuit is the total 80 that we have over here. So let me make this RT. So our impedance is going to be RT squared plus XL squared. So the RT is what I'm saying, that is the sum of 60 ohms over here and then the 20 ohms over here. So this is going to give us 80 ohms. Now our XL, which is the inductive reactance, is giving us 2 pi FL, and this is equal to 2 pi multiplied by the frequency 50, then multiplied by 159.2 times 10 raised to the power minus 300. So our inductive reactance, if we multiply everything over here, we are going to get 50 ohms. So now that we have this and then the total resistance, we can find the impedance for the entire circuit. So the impedance is going to be 80 squared plus 50 squared. So the root of all that we have over here is going to give us 94.34 ohms as our impedance. So now that we have the impedance, let's go ahead and find the current. So the B is saying we should find the current. So B, let me do it over here. We know voltage is equal to IZ. And so our current is equal to voltage over impedance. We know our voltage is 240, and then our impedance we just found to be 94.34. So if we compute everything over here into the calculator, we are going to get our current to be equal to 2.544 amperes. All right, so now that we've found our current, we found our impedance, let's go ahead and solve the rest of the questions. So let me get some space over here. All right, so let's look at the C aspect of this question. So the C is asking us to find the circuit phase angle. So to find the phase angle, we have tan. The phase angle is equal to, now because we've not found the voltage of the coil and then the voltage of the resistance, we can use that, because ideally this is supposed to be equal to V coil over VR. But because we do not have that, we are going to use XL over R. Okay, so the tan phase angle is equal to the XL, which is what we found earlier on, the inductive reactance, which we said we found out to be 50. So we have 50 over the resistance over here is going to be the total resistance. So from here is 80. So this means our phasor angle, or the phase angle, is equal to the tan inverse of the ratio 50 to 80, or 5/8. So our phase angle is equal to the tan inverse of this ratio is going to give us 32 degrees. All right, so now that we found the phase angle, let's go ahead and tackle the D aspect of this question. The D is asking us to find the potential difference across the 60 ohms resistor. So that is very easy. So VR over here is equal to IR. And then we already found our current, which I just erased previously. So we found that to be 2.544 multiplied by the resistance of the resistor over here, which is 60. And so that is going to give me 152.6 volts. All right, so let's look at E. The E is in the potential difference across the coil, V coil over here. Now, the V coil is going to be equal to the current multiplied by the impedance of the coil, V coil. Because the coil is not only having an inductor, it also has a resistor over here. So let me get some space and then we continue. So let me claim this over here. Okay, so how do we find the Z coil? So the Z coil, which is the impedance of the coil, is equal to the root of the resistance of the coil and then the capacitive inductance of the coil. Now, the capacitive inductance of the coil is equal to 2 pi. The frequency is 50. multiplied by the inductance, which is 159 over here. So we have 159.2 millihenry. So XL, if we multiply everything that we have over here, we are going to get 50 ohms as our answer. So now that we've been able to find this, we can do the substitution to find the impedance of the coil. So the impedance of the coil is equal to the root of our R is 20, so we have 20 squared, plus we just found our XL to be 50, so we have 50 squared. So if we compute these into the calculator, the impedance of the coil, which is Z coil, is going to be equal to 53.85 ohms. So now that we found that, we can find the V coil very easily. We already found our current to be 2.544 multiplied by the impedance of the coil, which we just found will be this guy. We multiply that with it, so it's going to be 53.85. So if you multiply 2.544 by 53.85, we are going to get 137 volts as the voltage or the potential difference across the coil. So thank you so much for watching. This is how we solve some further problems on an R and L series AC circuit. So thank you once again for watching, and I will see you in the next video. Bye bye.